Let's get started. So today we're going to cover another treatment step, which is sand filtration. Okay, or in short, we call it filtration. So it's related to membrane separation or membrane filtration, which we will talk about in our coming lecture. So both are filtration, but they have different characteristics. Okay, characteristics. So far we have covered coagulation, flocculation, right? And then sedimentation, right? Sedimentation. So at least 2 treatment steps. Now this is the third, sand filtration. Okay, sand filtration. So what is sand filtration and why? Why we do sand filtration? In my first lecture, we mentioned that water treatment is a multi-barrier approach, right? So multiple barrier, right? So multiple barrier. So why we need multiple barriers? Because we want certainty, right? We want safety, 100% safety. So you need to set multiple barriers, and these barriers protect human being from being, say, infected by waterborne pathogens, right? So we have multiple steps from the very beginning. We have screening, we have coagulation, flocculation, and you have a large sedimentation tank, right? Sedimentation tank, and all these steps we have learned they can remove suspended solids, pathogens to a certain extent. Okay, to a certain extent. So generally speaking, all these previous steps can remove suspended solids and turbidity from 60 to 80%. Right? So that is a large number, right? 60 to 80%. And these steps can reduce microbes, especially passed on pathogens, total coliform like E. coli, right? 70 to 90%. And virus around 80%. Giardia 60 to 90%. But the reduction is not enough, right? Not enough. We want more. Especially we want more removal of these microorganisms. We have covered this flocculation, coagulation, and sedimentation, and this is the typically the third, okay, main step, sand filtration. Sand filtration. So what is sand filtration? We have a short video. It's not a very good. I'm going to skip. So watch this by yourself. We have multiple videos, but we are here. Okay, sand filter. So what after sand filter? Disinfection, right? Disinfection. Our sixth lecture. And nowadays we could remove actually sedimentation tank and sand filtration by using membranes. Okay, by using membranes. So you save a lot of space and achieve high quality product water, but you have to pay more, right? If you use membranes. And membrane will be our next topic. So what we'll cover today, filtration overview. So what is filtration? What is filtration? And how we classify filtration. And what are the mechanisms? Filter materials, right? So we mentioned the sand. Sand is the most popular material because it's very cheap. And their parameters, how we characterize sand particles, for example, right? And calculate head loss in filters. And we have different types, slow sand filters and rapid sand filters. And what are the features for the 2 types of filters? And another very important operation, which is called backwash, okay, or sometimes backflush. Backwash. The operation is also used in membrane separation. Okay, so what is backwash? Okay, all the content is in chapter 11 of the textbook. Right, so we're still studying the first textbook on water treatment. Objectives: removal of fine particulates, so even smaller particles, even smaller. For example, residue flux after sedimentation typically lower than 0.5 NTU. Right. So what is NTU? NTU is a unit for turbidity. Right. If you do not remember, please go back to lecture 1. NTU. Okay, the unit for turbidity. And so we care a lot about removal of microorganisms. Right. Microorganisms. For example, Giardia, 2 log, right? Virus, 1 log. What is log removal? So generally, we say we have 90%, 95% removal, right? But here for microorganism, we use log removal. Okay, log removal. Log removal, log 10 over influent pathogen concentration over effluent pathogen concentration. So 90% removal is 1 log, right? 90%, 1 log. 99, 2 log. 99.9, 3 log, right? 99.99, that's 4 log removal. Okay. Right. So we classify filters into different types. The first criteria is the medium, right? So what is contained in the filter? You could have single media like sand or anthracite, right? Or dual media, anthracite and both anthracite and sand, and multimedia, anthracite, sand, and garnet. Okay, different size of sand particles. This one is really large, and at the bottom like this, right? Act as a support. So dual media filters are popular. It has longer filtration run. Available pore volume is maximum at the top. So this one, right? This one. The upper portion is coal, right? Lower portion is sand. So we have 2 types of filter media. and the pore volume gradually decreases to a minimum at the bottom of the filter. The conventional sand, you have also different sizes, right? Different sizes. Fine upper portion, then coarse sands, lower portion. Okay, right. And according to flow, so the media you have gravity, right? Gravity filters. The flow is driven by gravity, which is easily understood. Open to the atmosphere, flow through the media is achieved by gravity. We could also have pressurized. So the flow is driven by pressure. Fluid media is contained in a pressure vessel, right? And water is delivered to the vessel under pressure. Right? But typically for our membrane separation, it is driven by pressure as well. Okay, pressure. We have two typical types. The first one is slow sand filters. So the flow is slow. Flow is very small. Consists of fine sand supported by gravel. Right? So you have large particles at the bottom and fine particles, sand particles in the upper portion. Right? So you have very small pores. Right? Relatively speaking, small pores. So the flow is small. Slow sand filters, and it can capture particles near the surface of the bed. So imagine you have small space, right? So the particles cannot entirely get into the filter, but instead retain on the top, on the surface, right? And clean by scraping and replacing the top layer. Right? So the cleaning method is to remove the same portion, right, at the top. And the second type is rapid. Right? So you have larger sand grains supported by gravel. Therefore, you have larger spacing between the particles. Right? Because of large spacing, the flow will be higher, right? Will be higher, and you can imagine that the substances in water can get into the filter, right? Because of large spacing. Capture particles throughout the bed. So not only on the surface, but in the entire filter. Cleaned by backwashing. Okay, backwashing through the bed to leave out the particles. Right? So what is backwashing? Backwashing is pump flow in the reverse direction, right? So typically much higher flow rate. Okay? But we'll just mention this concept. We'll go to details later. That is based on the rate of filtration, slow versus rapid. According to flow control scheme, you could have constant rate, right? Constant rate throughout time. You have the same flow rate, right? But your driving force may change, right? So later we will see that we call fouling. The filter could be fouled. Right? Imagine the substances get into the spacing. You have higher resistance, right? Higher resistance. If you want to maintain the flow, you have to increase your driving force, increase your head, right? If you are using pressure, you have to increase the pressure to maintain the same flow, right? Otherwise, if you have the same head, you will have declining rate, right? Declining rate. And there you have to do backwashing or you have to do cleaning. Okay. According to the location of solid removal, depth filtration, solids are removed within a bed of porous materials, like rapid granule bed filters. Or cake filtration, particle removal occurs largely at the surface of the media through formation of filter cake, like slow sand filters. And these two are very similar to membrane separation. So basically, we'll encounter these problems in membrane separation as well. And then, so how we remove substances like microbes from water by filtration? We utilize different mechanisms, right? So what kind of mechanism you can think of? So how about size? Size? Yes, right? Imagine you have a lot of sand particles. We have sand particles, and they have different shape. You have different spacing, right? And of course, if you have larger particles, larger substances like E. coli, for example, here, right? When its size is larger than spacing, it can be retained. So that is size-based mechanism. Right? And when the particle gets into the spacing, right? It travels along the streamline, the flow streamline. The way it comes enough to the surface, it will be attracted to the surface. And this is interception. Okay, interception. This is the travel path, and here this particle will attach to this. For example, this is a sand particle, large, right? Because there is attraction between these two when they are very close, right? Van der Waals attraction, and this is interception. And there could be sedimentation. Right? So when there is gravitational force, it could also cause a particle to attach to the sand particle, like B, right? And also diffusion, especially when this particle is very small. Look at this schematic, right? So for particle C, it's very small, so its Brownian motion is important. Okay, then it moves around, and it has a probability to contact the sand particle, right? Sand particle, and it has a probability for the particle C, to stay on the surface. For some, it will bounce back, but for some, it will attach. Okay? And we have done some research on this, how the particle interact. What's the probability for different materials to attach, different particle to attach to certain surface. Okay, so this is diffusion. Interception Sedimentation is by gravitational force, and then diffusion. Diffusion is caused by Brownian motion. Right? Straining, right? Straining, like I said, is size too large to fit between spaces. Okay, too large. And fluctuation. Fluctuation. What is fluctuation? Particle attach and grow, right? Particles attach and grow. Original particle, pristine particle is small, but the 2 or more particles attached, they become large. And then the fluctuated particle or flux can be removed through different mechanisms, right? Through, for example, straining, through interception, etc. Okay. So earlier we're considering single particle, but now here fluctuation we consider the flux formed. Okay. Questions so far? No. Okay. So materials, what do we use? What can you think of? What criteria you should apply when you select? You consider efficiency, right? Efficiency. If you have a tank of these materials, can they effectively remove the substances you want to remove? So efficiency. Second, cost, money, right? So cheaper the better. Third, safety, right? These materials need to be safe by themselves, right? They won't be able to release toxic substances. They need to be stable, right? All these criteria you should consider, right? So so what wins the market? Coal and sand, right? So these are cheap materials. Sand, fine or coarse. So you have very fine sand, which can be used in slow sand filter, or coarse sand particles, which can be used in rapid sand filter, or they can be combined, right, in a single filter. And then coal, anthracite. Right? It's a specific type of coal. It has the highest carbon content, fewest impurities, the highest energy density. Okay, like this. Okay, like this. So this is sand. This is anthracite, and gravel. Okay, not considered as filter materials because they are large, right? They are large, and the spacing between them are large, so they can barely serve as a filter. So they support other materials like sand or coal. Okay, and here, so you probably have heard active carbon, right? So we use active carbon, this type of coal. Right. So desired quality, coarse enough to retain and hold back large quantities of fluctuated particles. Right. So the filter made of these materials needs to be effective. So coarse enough, you have certain desirable flow, right? Flow. And fine enough, you want to stop the particles, suspended particles. Right? If the spacing is too large, it's not effective. But if the filter is too dense or too compact, you have a very small flow, right? So that is not our goal. Imagine you need to trade sometimes hundreds of thousands tons per day, a huge amount, and deep enough to maintain relative long operation of the filter, right? And well graded to improve backwashing and cleaning. So what affect the filtration performance? The filter media, of course, the material itself, right? The composition and the size and the shape, right? The shape and size. We talk about size distribution. You cannot get a single size. It has a distribution. And porosity, okay, porosity. We talk about the porosity of the filter or even the porosity of the material. Right? The material could have pores. The filter, if the foam, could have porosity. And shape of the material, right? Typically it's irregular. It's not spherical. And the density, okay, density. The grain size and size distribution, the principal filter media characteristic that affects the filtration operation. And it affects clear water hair loss. So later we're going to calculate hair loss and build up a hair loss during the filter run. The smaller the size, the granule media, the smaller the pore openings. Right? That's imaginable. Smaller the particle size, smaller the opening. Small pore opening increase filtration efficiency. Right? You have very, very small pore. You can imagine almost everything will be retained, right? But in practice, it's not effective because the filter is going to be fouled very easily, right? You can have all these substances build up on the filter very easily. So you have to do very frequent cleaning, etc. That actually reduces efficiency, and we do not want to do that. Okay. And however, as the size decreases, hair loss through media increases. Right? You have very small flow, very small flow. Large size granule media, pore size increases and hair loss decreases. However, many of the small particles in the influent will pass directly through the bed. Right? Imagine this. So this is small media, this is large media. Look at the spacing. Right? And this spacing is the channel for the water to get through. Right? Get through. How to characterize the filter media? Effective size. D sub 10. Effective size. Same opening size in millimeter, so the unit is millimeter, which permits 10% of media by weight to pass. Right? How we do this? We do a saving experiment. You have saves with different opening size, right? and you do the saving and measure the mass. And the first is effective size, d sub 10, and second is uniformity coefficient. What is uniformity coefficient? D sub 60 over D sub 10. What is D60? Save opening in millimeter, which permits 60% of medium by weight to pass. Right? So one is 10%, one is 60%. The higher you see, the larger size distribution. Right? As you say increase, non-uniformity increases. And both determined by save analysis. Save analysis. Let's look at this slide first. Right, so here we have different saves. At the top, you have large opening. Bottom, you have smaller opening. Right, smaller opening. And particles with different sizes will be retained on different filters. Right, so they are large, they are small. And measure the weight and the weight ratios. Right, largest opening on top, smallest opening on the bottom. Medium is placed on the top save, and the stack is shaken. At the end of shaking period, the mass of material retained on each save is determined. The cumulative mass is recorded and converted into percentages. And cumulative frequency distribution is plotted. What you would get, this is one example. Right, so a curve like this, The x-axis, you have the save opening, right? Save opening from, so this is reverse direction. The right, smallest opening, right? So the left, the largest, and you plot, and this is cumulative percentage. Therefore, right, the highest, the top, the most top is 100%. 100%. You get this curve, right? And D sub 10, 10%. You have a size. D60, you have a size, right? And uniformity coefficient D60 over D10. This is 1.27, right? Okay. So uniform grounding media, what's the benefit? Permit deeper penetration of lock. Okay. So better utilization of storage capacity of the bed. And moreover, during backwashing, cleaning of media with water in reverse direction flow can be easier. Right? Non-uniform media, the bed will stratify with smaller particles, and there will be small pore opening at the top. And the save number is how many saves per inch. And we will get data like this if you do the save analysis, and we plot, we get this curve. And then from the curve, we can get D10 and D60. Right? One example. If you have a laptop, which is much better, right? You have save number, and you have the opening and weight processing. This is actually already cumulative. And you are asked to calculate D10, and you see uniformity coefficient. Five minutes, 10 minutes. I guess many of you do not have the tool. Right? You need Excel, which is better. Right? So x-axis, the size, the safe size, y-axis, the weight percentage. Right? You plot all these data points here. Right? And D10, 10%. You have a size. 60, you have a size. Right? So the uniformity coefficient is 1.43. do this very often because we're engineer, right? Okay, plot. Not very difficult, but a little bit time consuming. And the shape. So we talked about the size and also the shape, right? The shape filter grains are important because it affects backwash flow, the porosity, right? Porosity, the filtration efficiency. The useful measure of shape is sphericity, how spherical it is. Spherical it is. And sphericity of the filter materials equals surface area of sphere have same volume with particle over surface area of particle. Right? For sphere, the equation to calculate the volume is this. Surface area is this. Right? For an irregular shaped particle, it will be this. Surface area of sphere having the same volume with particle over surface area of the particle. So this is the imaginary particle, imaginary sphere particle, same volume. And this is the surface area of the real particle. Right? And then porosity. Epsilon, right? It's a fraction, so it does not have unit. Void volume over total volume. Affects water necessary for cleaning the filter bed. Affects the head loss. As the particles become less spherical, when phi is reduced, porosity of a given volume increases. Right? So here we compare 3 types of materials: silicate, like sand, anthracite, right? The hardest coal, and granule active carbon. So 3 types of materials. Their density, density. So sand, silicate has the highest density. These are the carbon, right? Carbon, and porosity, epsilon, and the phi. Right? Okay. Any question? No. If not, let's take a break. Okay. So what's next? Let's consider some filtration hydraulics. In particular, the clean bed head loss. As we mentioned earlier, we have different types of flow, like laminar flow. Right? The Reynolds number is smaller than 2. And here we could utilize an equation which is called Karman-Kozeny equation to calculate the head loss. Right? The Reynolds number is smaller than 2. In a transitional or turbulent regime, Reynolds number is larger than 2. We have different equations, Ergun equation or Rose equation, but we're not going to discuss this in our course. Right? So we primarily focus on laminar flow. Reynolds number is smaller than 2. And here we simply use Karman-Kozeny equation. Right? So fortunately, through a flow through a clean filter of ordinary grain size, the size is between 0.5 and 1 millimeter, and ordinary filtration velocities 5 to 12 meter per hour will be in the laminar region. Right? Laminar region. So the most relevant equation is Karman-Kozeny equation. And what is Karman-Kozeny head loss equation? This is for uniform media. Right? So delta H is the change of head loss. The unit is length, right? Meter, inch, feet, etc. Delta H over delta L. L is the depth of the filter. Okay, depth of filter. Right, 2 times mu, and V C sub C. What is V sub C? Is V is surface loading rate. What is surface loading rate? Surface loading rate is Q divided by A sub S. Right? Sedimentation is the same. It's Q divided by AS. Superficial velocity or surface loading rate. Okay? VC is V divided by epsilon. Epsilon is the porosity of the filter. Okay? And VC is average pore with velocity and cannot be measured, and we use this equation. Okay? Rho is the density, G gravitational, right? Acceleration, 1 over RH. R is the radius of the filter media. Okay, filter media. But this is a hypothetical spherical particle, but in reality it's not, right? So we need to connect RH with sphericity. Fine, right? This is sphericity. Anyway, this equation can be transformed into this one. Okay, we plug in this and RH. And C is a constant depending on the definition of the friction factor. The C is a friction factor. And typically we use 5. Right. We do have a very complicated example. Which RH is the radius of the particle. So let's look at this example. The design of the filter, standard filter. First one, we know the Q, right? Design flow is 24 million gallon per day. So that's Q. Filtration hydraulic loading. What is this? It's the first time we say this concept or this definition. Filtration hydraulic loading. If you do not understand this, you just look at its unit. Gallon per minute per square feet. That is a unit of surface loading rate or superficial velocity, right? Gallon per minute over some area. So this is superficial velocity. Determine the total filter area. This one is easy. right? That's from the definition of loading rate, surface loading rate. And next, select the number of parallel filters needed, and their lengthwise. If each filter is square, the length equals the width, right? With area between 450 and 650 square feet. Right? And B shows a dual media filter consisting of 20 inches of anthracite, effective size 1.1 millimeter, over 12 inches of sand. You have two, because dual media, you have two composition, right? One is anthracite, one is sand, and effective size 0.45 millimeter. Porosity of the anthracite layer is 0.4, that is epsilon, okay? And sand porosity 0.36. Determine the superficial filtration velocity, that is V, and pore velocity, VC, right? That is VC equals V divided by epsilon. In both anthracite and sand layers, in both feet per minute and minute per hour, the two different units. Calculate detention time, HRT, right? HRT. Q divided by V. Oh, sorry, V divided by Q, right? V divided by Q. But what is a V here? And then calculate the head loss. You have to use Carman-Kozeny equation. Temperature. Why we need to know temperature? Because you have to use the viscosity, right? Viscosity. The design hydraulic loading rate. And if you change the filtration rate, superficial velocity, what is the Klein-Bradley loss? And what if you change the temperature? What is the loss? And if the entire filter depth was sand of the same size, and what would be the head loss? Right, so a lot of calculations. 15 minutes. To start from problem A, it's very basic, and then to the use of Carman-Kozeny equation. Of course, you have to find some numbers for viscosity. You have to Google, okay, under that temperature, viscosity for water. Be aware of the unit you use, okay? Gallon per minute, square feet. If you use the value for viscosity, you have to use the same. I guess you can have some discussion among yourself regarding what equation you can use, what the values for viscosity, etc. That may help accelerate our pace. How many of you have reached step D, problem D? No one? All right. So let's do this step by step. We first look at solutions to the first few problems. Then I still want you to calculate using Karman-Korzeny equation because that's important. But you need to solve the previous few questions to reach that step. Right. The first question, right? It's basically you have the superficial velocity, right? You have the q, and you get the surface area first, right? So that is the A total. What is A total? What is A total? It's AS, right? A sub S, right? Surface loading or superficial velocity. This is A total. Okay. So everyone knows this step, right? Just make sure everyone knows what we are doing here. So V, also we use the V naught, but it's V is superficial velocity. And this is the total surface area you need for the filter, right? Total filter. And the area, each filter area is between 450 and 650. 450 and 650. And right, so you have a narrow number to choose, and we choose 8. Choose 8, and each will be 520 square feet. 520 square feet. Of course, the combined number will be similar to this, right? 520 square feet each. And because the tank is square, right? So the length and width is about 23 feet. 23 feet. Of course, you have option to choose 7 or 9 filters. If you have more filters, the size will be smaller. Right? Fewer filters, the size will be larger. Okay. So how many reached any of this? Any of this? Did you? No. So which step were you stuck with? What number you get? 9. So this one. Okay. All right. So that's the first step. First step. So you see that for our problem, we have some flexibility, right? You have certain freedom to choose certain parameter. Sometimes there is more than one solution. Okay. And what is the second problem? I choose the media. Right. You have 2 media. One is anthroposide, the other is sand. And you are asked to calculate superficial filtration velocity and pore velocity. What is superficial velocity? That is surface loading rate. Right. Surface loading rate. Right. So for the first question, superficial velocity, it's just this one. What we are doing here is just to convert the unit. Convert a unit from gallon per minute per square feet into feet per minute, because this is required. Right. And the value is given to you. It's 4. Okay, it's 4. And here we convert gallon per minute per square feet into feet per minute, and then to meter per hour. Okay. These 2 steps, we're not doing any calculation. We're just converting the unit. Superficial velocity is given. It's just 4. Okay. And pore velocity. How can we get a pore velocity? What is the equation? Pore velocity. So tell me, what is the equation? Vc equals V naught here divided by what? Epsilon, right? That's the porosity. That's porosity. We do not have a step here, but we have the solution. Right? Porosity is this number. And how we get the 1.33? This one, right? 0.53 divided by 0.4. You get a 1.33. Okay. For the sand, the porosity is 0.36. Pore velocity is 0.53 divided by 0.36. It is 1.47. Okay. You use the same method to calculate pore velocity in meter per hour. Right? They have the same value, but they have different units. They mean the same thing. Okay. Question? You have any question? No? You calculate this? This is conversion unit. So 1 meter is 3.3 feet. That is unit. Convert unit. 1 meter is 3.28 feet. It just changed the unit. This one is 1 cubic feet equals 7.48 gallon. Conversion unit. This is superficial velocity. You can use this, but here you're asked to get the value in feet per minute and meter per hour. Okay. For the first step, there is no calculation. Detention time. Detention time. All right. So what do we have here? So we say that detention time can be calculated V divided by Q, right? V divided by Q. It could be also the length divided by the velocity, right? The length divided by velocity. So here we have the bed depth divided by the pore velocity. You also get time. You also get time. Therefore, the hydraulic time is 1.25 minute. And this is for the anthracite layer. And for the sand layer, right, the same length, the same depth, but the pore velocity is a bit different because of the porosity, and it's 0.28, 0.68 inch. Can anyone check this for me? If you use the same 20 divided by 12, then divided by 1.33. Can we get 0.68 here? It's different. 0.68. 1.13. It's 20 divided by 12 divided by 1.47. 1.13, right? So this one should be 1.13. 1.13, not 0.68. Or the depth, is the depth the same? Oh, it's 12. All right, so let's so it's 12 divided by 12, right? The depth is 12 inch. It's not 20 inch. The 12 divided by 12 and divided by 1.43. This number should be okay then. 0.68 minute. And in total, detention time is 2 minutes. How do you think? It's fast, right? So only remains in the filter for 2 minutes. It's very fast for standard filtration. Okay, shall I move next? Next what? Okay, now I want you to work on this. Hair loss. Because you have not done so, but you have know all the parameters from previous calculations. So please do this one. Just do D. Okay. Use the Kalman-Cohen equation. Temperature 68, file height. Okay. Check the viscosity under this temperature. Design hydraulic loading as 4 gallon per minute per square feet. Right. Get the hair loss. You have obtained almost all the data from previous set. Farmer-Cosini equation. So here, kinematic viscosity is dynamic viscosity divided by rho, density. Okay, density. And you need Google to get all these values of viscosity. I do not have the steps. I gave a table of answers. Problem D is here. So when you calculate that, you have to separate the two layers, anthracite and sand. The total head loss will be the combination of the two. Okay. So please do the calculation after our class. Now let's take a break. 应该是 international meter. Okay. Shall we continue? Let's start. Let's continue, and let's aim finish early. All right, we have some 15 slides. Let's finish in 20-25 minutes. Next, let's talk about the two types of filters, sine filters, slow and rapid, their features and their application scenarios. The first type is slow sine filter, right? It's typically used in rural areas, especially in developing countries. Water is purified at low velocities, 0.1 to 0.3 cubic meter per hour per square meter. Right? So the velocity is very small. The retention of suspended matter in the upper 0.5 to 2 centimeter. Right? Duration between two successful clean a few weeks to months. Let's take a look at the schematic. Right, so this is the slow filter, sand filter. Bottom some gravel as support, right? And the water flow is downward. Okay, it's downward. It's downward. At very top, there is a layer called this is the German word, Smartodecki, right? A thin film. Okay, thin film. Look at the history. Slow sand filtration, 100 year, right? Rapid, only 50 year. And it has much lower velocity, hydraulic loading rate. Q over AS is between 0.12 to 2.25 meter per day. Okay, look at this number. It's smaller than 1. Right? Later you can compare this number with that of rapid sand filter, lower than 0.5. Rapid filter here larger than 5. Right? Larger than 5. No chemical pretreatment. Application low turbidity surface water. Right? So it's relatively good. The raw water. There's a clogging layer on the surface, okay? And that is for the screening of turbidity and bacteria. What does it look like? Right, this kind of huge, right? And there will be biodegradation of some DOC, like 10%, because of the bacteria growing on the top layer. Okay, like 10% degradation of dissolved organic carbon, and the run length operation is 30 days. Okay, about 30 days, 1 month. But for rapid sand filtration, it's about 4 days, a few days. Right? So why do we restore the performance? So we do not do cleaning here. It's not cleaning, it's just the scraping or removal of the top layer. Simply scrape off. More applicable to small systems because you typically need a large land, right? Large land. Some pictures, right? Very large kind of filtration. Disadvantages: large space requirement, frequent, cleaning, malfunction on treating high turbidity water because you can see it can be very easily fouled if you treat high turbidity water. Right? So typically we use it to treat low turbidity surface water. Cleaning, removing the top few centimeter of sand. Okay. So rapid sand filter, what we can say in the water treatment plants, okay, is rapid sand filter. This is filtered water. This is without water. There's a sand, right? Sand. And if you go to Shatian water treatment works, you can see carbon, active carbon as well. Okay. The design, you consider the filter media here. We have sand, right? And the support and under drain. And for rapid sand filter, very important operation is backwashing. Okay, backwashing to remove suspended material that has been deposited in the filter during the filter cycle. Rapid sand filter schematic, right? Surface wash unit, the filter media, graded gravel as support, the under drain blocks, right? The outlet main. Filtration rate, right? We say that larger than 5 to 25 meter per day, 5 to 25. Slow sand filter lower than 0.5. Right? So multimedia becomes more popular. Instead of sand, you have coal, right? Individual module size, typical treatment capacity 20,000 cubic meter per day. 20,000 cubic meter per day. So a large capacity. The depth, right? 0.64 to 1.3 meter. It's actually 24 to 48 inches. Okay, inches. And 2 meter for deep media. Duration 12 to 94 hours. Right. So backwash. Backwash, what do? You pump water from the bottom to the top. Right. So it's reverse direction. And here you have higher flow rate. The head is 1.5 to 3 meter. Okay. The superficial velocity 37.5 to 75. Compare this value with the operation 5 to 25. Right. A few times. The time 10 to 30 minutes. There will be expansion of the sand layer. The depths will become 30 to 50% thicker. Okay, during the backwashing. So when to the backwash, if the water applies to a filter is very good quality, the filter runs can be very long. We need backwash to remove the captured particles. And when increase of head loss across the filter, deterioration of filter water quality, and maximum time limit. Number of ways: water backwash with full fluidization of the sand, and surface wash plus the bad wash, and we could also use air scour. And how backwash water is introduced into the bottom of the bed through under drain system. Backwash water should be turned on gradually to avoid disturbing the gravel layers. The backwash flow is continued with full fluidization until the waste wash water is reasonably clear. The rate expansion of the bag, sand bag, is a wake washing method. Surface wash plus fluidized bed wash. So here you have surface wash. Surface wash system inject jets of water from orifices located about a few centimeters above the bed surface. Surface wash operates 1 to 2 minutes before the upflow wash. Terminate 2 to 3 minutes before the end of the upflow wash. Air scour. Supply air to the full filter area from orifices located under the filter media. Must be applied before the water backwash. We do have a video show. Air scour. Right, so we have seen a full video. Treated water from storage is used for the backwash cycle. All right. we need a head, right? Water head. The flow rate has to be great enough to expand and agitate the filter media and suspend the flux in the water for removal. But be careful, the filter backwash rate is too high. Media will be washed away, right? Washed away. You have to control the backwash rate. Hydraulics, 1 to 5% of produce will be used for backwash. Right? The purpose to obtain bad fluidization and expansion. Right? You typically need 15 to 30% the bad expansion. Aeration increases shear force to remove deposited particles. You have seen in the video the aeration. The efficiency, we know this already, right? Superficial velocity, and filter efficiency. Net rate of water production. Volume of water filtered minus volume of water used to backwash minus volume of water used to rinse the filter after wash. Right? After wash. So that is a net rate of water production. The pathogen removal efficiency, we care about pathogen very much. Look at this. Sand filtration. Right? Compared to coagulation and sedimentation. The virus. Compare. This is input. This is settled water after sedimentation. This is filter water. Right, filter water. And you can calculate the log removal from this number. All right. So for today's lecture, what you should be able to, you should understand filtration mechanisms. What are the filtration mechanisms? Interception, sedimentation, diffusion, straining, etc. Right? Common filter media materials, and their parameters. Calculate simple head loss. So we use Carmen-Cozzini equation under laminar flow. Right? Under laminar flow. So for the practice problem, please do after this class. I've given you the answers already, but no steps. So please use the Carmen-Cozzini equation to calculate practice problems. And describe those sand filters and rapid sand filters. What are the features, right? Like superficial velocity, and what are their applications? Right? Compare it to, and what are the cleaning methods for each of them? And understand, describe backwashing of rapid sand filter. Right? So for slow sand filter, we do not have backwashing. Rapid sand filter, we have backwashing. So what happens during backwashing? Okay, you should be able to describe all this. Okay, it's quite clear. Learning outcomes. All right. So that's for today. I'll see you next week.